All right. Hello, AP Stats. Here's what we're going to talk about today. We're going to talk about binomial distributions. Now, first thing we need to talk about whenever we talk about binomial distributions is this idea of a binomial setting. What that basically means is that there's certain times when you can use a binomial distribution and certain times when you can't. Here's how you can kind of tell. You have to ask yourself basically 4 different questions, and there's an acronym that we use to kind of help us remember that. It's BINS. B-I-N-S. Here's what each of those stands for. The first one, which you have to ask yourself, is whatever you're dealing with binary. I'll talk about what that means in just a second. The second thing you have to ask yourself, are my trials independent? Third thing you have to ask yourself, is there a specific number of trials that we're going to be looking at? And the last thing is there a clearly defined success ratio? In other words, is the probability of success the same for each? So just as a reminder, here's kind of what we're looking at for binary. Basically what that's asking is, can each trial be classified as a success or failure? Second thing, with independent, basically what that's saying is, if you know one outcome, does that influence future results? The third thing you have to ask yourself, the number. Is there a specific number of trials? In other words, the number of trials needs to be a fixed number. And the third thing, or the fourth thing, final thing, is success. There needs to be some probability so there is some probability that is fixed. Okay, so binomial random variable, let's kind of talk about what that is. Basically, when you talk about a binomial random variable, the success or the count x of successes in a binomial setting is a binomial random variable. Now, one thing that you do have to have, your number of successes x needs to be less than or equal to n, which is your number of trials, and also has to be greater than or equal to 0, meaning you can't have any negatives there. Okay, so now let's talk about some binomial distribution parameters, some of the different kind of numbers we're going to be working with here. So one of them that we just kind of mentioned was n. N is the number of trials of some chance process. Another thing we're going to talk about P. P is just the probability of success on any one trial. Okay, so what we're going to do in this first example, we're going to determine whether the random variables below have a binomial distribution. In other words, can we use kind of our binomial distribution to represent each of these? So, in essence, what that's asking for in this example, what we're going to do for each of them, we're going to do basically a BINS for each. Okay, so An example, part A. It says roll a fair die 10 times and let x equal the number of sixes. Okay, so let's ask ourselves first, B, is this binary? Can you classify each trial as either a success or failure? And basically you can. You can say that success would be any roll of a 6, and you could say that failure was any other number. Basically just not a 6. Second thing you have to ask yourself, would each trial be independent in this case? And dice rolls are independent. One dice roll doesn't affect the next one, so because dice rolls are independent, we can go ahead and fulfill the I part of Ben's. Next thing, N, is there a fixed number of trials? And we said that there were 10 times that we were going to roll the dice, so it checks out there. And then lastly, S, is there a fixed probability of success? And there's a 1 out of 6 chance of rolling each 6. So, for the first one, can we use a binomial distribution in this case? The answer would be yes. Okay, let's look at part B. Maybe it's a little different. It says we're going to shoot a basketball 20 times from various distances on the court. Let y equal the number of shots made. So our first question, we're going to ask ourselves, is it binary? Can we classify each as a success or failure? And this one is pretty easy to say yes. A success would just be any make. A failure would be any miss. Second thing we have to ask ourselves, is each trial independent? And the answer here, yes. Each shot would be independent. Making one shot doesn't necessarily make you more or less likely to make the second one. Alright. N. Let's see, it says that we're going to shoot the basketball 20 times, so there would be our fixed number of trials would be 20 times. And now let's look at S. What is the probability for each success? And in this case, we don't know. Each one, it says, is going to be at various distances. It's not saying that we have a 20% free throw shooter or a 30% three-point shooter. So really, we don't know the probability of each success happening. So that's kind of a problem. This is not going to be one that we can use a binomial distribution for. Okay. For part C, it says observe the next 100 cars that go by and let C equal color. First thing we need to ask ourselves, is this binary? Well, success and fail, really there is no way to know what that's going to be. All we're going to do is write down what each car color is. We didn't specify that we're looking for any particular color, so without going any further, we can just go ahead and say no for this one. Okay. Now, we're going to actually see how we can use some of this information to model some binomial distributions. Alright, so in this example, and basically what this is going to lead us to eventually, hopefully, is going to be kind of seeing a formula for calculating a probability for a binomial distribution. So, in this example, in many games involving dice, rolling a 6 is desirable. The probability of rolling a 6 when rolling a fair die is 1 out of 6. If we're going to let x equal the number of 6s in 4 rolls of a fair die, then x would be binomial. It says with n equals 4 and p equals 1 over 6. So, be very important here. N equals 4, p equals 1 over 6. In part A, it says what is the probability that x equals 0? In other words, that is, what is the probability that all 4 rolls are not 6s? So, when we look to calculate this, we're looking for the probability that x, the number of 6s rolled, is 0. In other words, another way you could say that that would be the probability of failing 4 times. 4 failures would be 4 6s, none of which, or 4 non-6s, so that would be 4 failures. And the way we do that, remember, they would be independent. Basically, that would be a 5 out of 6 chance of failure. And if we went to calculate that 4 different times, we would use an exponent of 4 to say we're going to take 5 over 6, multiply by 5 over 6, multiply by 5 over 6. And when you put that in a calculator, you find out that the probability that there are no 6s rolled at all would be 0.48225. So a little less than a 50% chance of not having any 6s show up. Okay. Now in part B, things get a little more interesting. What is the probability that x equals 1? In other words, what is the probability that you get exactly 1/6? Okay, so what that could look like, you could say the probability that x equals 1, if we listed those out separately, you could say that would be a success and then 3 different failures, which to calculate that probability of a success would just be 1/6, which you could say to the first power if you wanted to. And then there are 3 failures, so similar to how we calculated the 4 failures, that would just be 5/6. This time we're going to raise to the third power, and we type that into a calculator, we get 0.09645. Now, what we need to think about, the success, it doesn't matter where that happens. It could be the first roll, it could be the second, it could be the third, it could be the fourth. In other words, you could have success and then 3 failures. You could have a failure, success, and then failures. You could have the success be in your third trial, so that would look like this. Or you could have the success be on the very last roll. In other words, the success, it could be in basically 4 different places. There are 4 different ways that you can have a success exactly once. So this probability is great, 0.09645, but keep in mind that there's 4 different ways that can happen. In other words, what you'd have to do, you'd have to multiply by 4 to say that there's actually a 0.38580 chance that you roll exactly 1/6. Okay, so what we're going to do, we're going to kind of continue with this. What eventually we're going to hope to do is be able to create a probability distribution. So what we're going to do, now let's look at what's the probability that x is equal to 2. In other words, the probability that you get 2 6s, or the probability that x is equal to 3, where you'd have 3 6s. And then what's the probability that x equals 4? In other words, all 4 of the different rolls giving you a 6. Okay, so let's take each of these kind of piece by piece. The probability that x is equal to 2. In other words, what one example that could look like would be to have success followed by failure, which to be able to calculate that, remember successes would have a 1/6 chance. If there are 2 of them, we'll raise to the second power. Failures, there's a 5/6 chance, and there are 2 of them, so again we'd raise to the second power. This would give you a probability of 0.01929. Now, in terms of all the different combinations that will give you 2 successes, it turns out that there are 6 different ways, 6 different orders in which you can get 2 successes, whether that's success, fail, fail, success, 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 fail, 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 success, success. If you wanted to, you could list all 6 out, but I'll just kind of help you out here. There are actually 6. So to calculate the overall probability that you have 2 6s, we need to take our probability of having the 2 successes first, multiply by the 6 different ways that that can happen, would tell you that there is actually just a little bit more than 11% chance that you roll exactly 2 6s in a trial of 4. Okay, in a similar way, let's calculate the probability that x is equal to 3. One possible way that that can happen would be to have 3 successes in a row followed by a failure. To calculate that probability, remember success, 1/6. This time we raise to the third power. For failures, that would be 5/6, raising to the first power. There are a total of 4 different ways for this one, so we'll have to multiply whatever the probability is that we get by 4. And for this one, you get a probability of 0.003858, which when you multiply by 4 here, 0.003858 multiplied by 4, you get that there is a little more than a 1% chance, 0.015432, that you roll exactly 3 6s in 4 separate trials. The last one we're going to find, probability that x is equal to 4, keeping in mind that you could, if you wanted to, calculate this just by taking 1 minus all the other probabilities that we found. But just to be consistent with kind of the method we've been using and to hopefully kind of start to notice a pattern, that would be the probability of 4 successes, which would basically be 1 out of 6 raised to the power of 4, which for this one gives you 0.007716, and it turns out we can actually leave that as our probability. There's only one way that you can actually get 4 successes, which is the one we just mentioned, so we really don't have to multiply by anything other than 1 if you really wanted to. So this leads us into a couple of different ideas. The first being the binomial coefficient. Basically what that is, that's the number of ways of arranging k successes, however many successes you want, among n observations. What that looked like in our examples, basically where we were talking about how there were maybe 6 ways that you can get 2 successes or 4 ways that you can get 3 successes, that's basically what we're looking at in terms of the binomial coefficient. The way we say that, the way it's read, we will usually say that as n choose k. Now, there's actually a formula that can actually help us so that we don't have to list out all of the different ways that we can get a certain outcome every single time we want it. Here's how we do that. We say n choose k. We write it as n over k and use a set of parentheses. The way it's calculated, it's actually calculated using what's called a combination, which is written as n capital C k. Now, the actual formula for this, in case you want to actually calculate it by hand, you take n factorial divided by k factorial, and then multiply by, in parentheses, n minus k factorial. Factorials, just as a refresher on those, in case you need to kind of refresh on how to do those, if I wanted to find 3 factorial, that would just be taking 3 times 2 times 1. You basically just take whatever the largest number is and multiply by each whole number less than that number. Now, that's a lot of calculations to do. We are usually not going to go through all those calculations. If you ever want to find this button right here, here are the buttons you would press on your graphing calculator. You would go to Math, over to Probability, and then it is option number 3 for you, where it says 3 and has NCR. So your calculator uses R instead of K. It still works just the same. And if you wanted to actually calculate it using factorials, you can see that the factorial button is just option number 4. But the good news is we're going to be using our calculator pretty much any time we need to calculate this. So again, those buttons, you go to Math, over to Probability, and option number 3 would basically let you type in your combinations. Okay, so now, the moment you've all been waiting for, here it is, binomial probability formula. Basically, if x has the binomial setting, in other words, it fits the model, it passes our bins question that we were asking. So if x has the binomial setting, with n number of trials, and p equals the probability of each success, and k is any one of the values then here's what we get. Here's our formula. The probability that x is equal to some number k. You take n choose k multiplied by the probability p raised to the power of k, and then multiply that by 1 minus p to the probability, or to the power of, I should say, n minus k. There it is. Now, another way that you might see this sometimes, you might see it instead as n choose k, p to the power of k, multiplied by q to the power of n minus k. Basically, q is the same as the complement for p. In other words, if you take 1 minus p, you get q. So sometimes you might see that notation show up from time to time. Just know it's the exact same formula. Okay, so now here's how I kind of want us to end today. I want us to go ahead and list out the probability distribution for x from our example from earlier. So here would be our probability distribution for x, which again, remember, was the number of 6s that were rolled in 4 trials. So we had x, and we also calculated all the probabilities, p sub x. And for our outcomes, we could either roll 0 6s, we could roll 1 6, we could roll 2 6s, 3 6s, or 4 6s. The probability for each of those happening for 0 was a 0.48225. Probability that there was exactly 1 6 rolled was 0.38580. That there were 2 rolled was 0.11574. For 3 rolled was 0.015432. And for exactly 4 rolled was our last one we found, 0.007716. Now, just to kind of show you something that I think is kind of cool, kind of connect some dots for you. If you think about k, which remember represented the number of possible ways that each outcome could happen, for 0, there was only one way that you could get 0 6s. There were 4 different ways you could get 1 6, 6 different ways you can get 2 6s, 4 different ways you can get 3 6s, and just 1 way that you can get 4. This actually is related to Pascal's triangle, which you can actually use for binomial expansion. Basically, for Pascal's triangle, starts with a 1, has 2 1s on the first row. So this would be row 0 where it starts. Here would be row 1. Row 2 would be a 1. You add these 2 1s together to get 2, and then another 1. And then each time you go down a row, you add together the 2 numbers directly above it. So 2 plus 1 would be 3, 3, and then 1. The next row would start with a 1. 1 plus 3 would be 4. 3 plus 3 would be 6, a 4, and a 1. So what's kind of cool about this triangle, you've got row 0, row 1, here would be row 2, here would be row 3, here would be row 4. Notice that we had 4 different trials that we were going to do. And the number of ways each one could happen actually match up perfectly with these numbers right here, which I think is kind of cool. So if you were going to do 5 different trials, basically what you could do, keep the triangle going, you'd have 1, 5, 10, 10, 5, and then 1. Basically what that would tell you is that there's one way to get no 6s in 5 rolls. There are 5 different ways to get 1 6 in 5 rolls, 10 to get 2, 10 to get 3, 5 to get 4 6s, and then there's one way that you can get all 5 rolls to be a 6. So it's kind of cool, and it's again something that we hopefully have seen before, maybe in Algebra 2, where you did some binomial expansion. But that's kind of the last thing that we had to talk about today. Okay, so here's kind of our plan for the rest of this week. On block day, we are going to go over your quiz that you took in class yesterday, as well as kind of add in some more notes on binomial distributions. So we'll kind of wrap those up by looking at how we can use graphing calculators to help us even more than they already are. That'll be kind of what we look at on block day. Friday is going to be a shortened day Just as a reminder, on Friday we're going to talk about the geometric distribution, and that'll be pretty much the end of the notes. So keeping in mind, test is going to be after Thanksgiving break. It'll probably be either the Tuesday or the block day after Thanksgiving break. Haven't quite decided yet when we're going to do that. But just know that there is still that extra credit, which has been posted since the beginning of the unit, that is due on test day. And I'll be able to tell you by the end of this week what that test day is. That way you can make sure you're prepared for that. But just know that extra credit that you've been working on, hopefully, is going to be due on test day. I will be back with you guys on block day, so if you have any questions over what we talked about today, please be ready to go over those at the start of class on block day. And that's all we've got. Have a good rest of your day, guys.